Hello, welcome to the course SJPHY1C01 Properties of Matter and Thermodynamics. The contents of today's lecture is taken from Heat and Thermodynamics by Brijlal and Subramaniam. Today we are going to discuss topics from Chapter 4, Thermodynamics. There are two major branches of thermal physics. One is thermodynamics and another one is statistical mechanics. Thermodynamics is a branch of science which deals with heat and temperature and their relation to work and energy. So in particular, it describes the interconversion between thermal energy and other forms of energy, like mechanical energy, chemical energy, or electrical energy. For example, in the case of heat engines, the thermal energy is converted into mechanical energy. Similarly, in the case of thermal power plants, the thermal energy is converted into electrical energy. So thermodynamics deals with this kind of interconversion between different forms of energy. Thermodynamics usually doesn't take into account the atomic constitution of matter, like what are the types of atoms or molecule, or what is the lattice in which the atoms reside, etc. It only deals with large-scale response, which is known as macroscopic properties of the system, which we can observe and measure. So this is the fundamental characteristic of thermodynamics. It only deals with macroscopic properties or bulk properties and usually doesn't get into the microscopic detail. For example, when I say that I have 1 liter of water, I am supplying some heat energy to it so that its temperature goes to the boiling point. Okay, so here you only talk about the temperature of 1 liter of water as a whole. You don't go into the details of each water molecule, how much heat energy is acquired by each water molecule, what is the response of individual water molecule, how their velocity is going to change, how their internal energy is going to change. You are not going into the atomic details. You are only going into the bulk details here. On the other hand, if you want to get a better picture of the microscopic properties of a system, then you will have to resort to another branch of thermal physics known as statistical mechanics. Here, you are primarily exploring the microscopic properties of individual atoms and molecules and connect these microscopic properties to the macroscopic properties of the system, which we can observe and measure. So here when I say I am providing heat energy to 1 liter of water so that it rises to the boiling point, now you can try to analyze what happens to each individual atoms or molecule. Typically, when you provide heat energy, the velocities of the individual molecule is going to increase. When velocity increases, the kinetic energy of the molecule increases. So you can understand all the processes happening in the system from a microscopic point of view. Similarly, suppose I am shining light onto a piece of silicon. So I can go to each silicon atom and understand what happens in response to the light. So typically what happens is the electrons in the atoms get excited. They are going to occupy different energy levels. So once you understand the electronic distribution inside an atom, you can connect this to the different properties of the material, like the electronic properties, optical properties, magnetic properties, etc. So in some cases, you need to understand the microscopic structure of the material or microscopic properties of the material. There you use statistical mechanics. In some cases, you are happy with the macroscopic properties or the bulk properties. There you are going to deal with thermodynamics. So if you look at the hierarchy here, the matter usually consists of molecules. Molecules are made of atoms. Inside atoms you have electrons, protons, neutrons, etc. These are extremely tiny particles, so their behavior is governed by quantum mechanical principles. So you use quantum mechanical principles to understand their microscopic properties. This is statistical mechanics. Once you understand the microscopy properties, you connect it to the macroscopy properties. This is the realm of thermodynamics. And after this, you can connect this to all the chemical and physical properties. So this is typically a bottom-up approach where you move from a microscopic domain to the macroscopic domain. It's important that we have a rough idea about the order of magnitudes involved here. So under normal conditions, the typical distance between particles in solids or liquids is around 3 angstrom, which is 3 into 10 to the power minus 10 meter. So if you take 1 centimeter cube of solid or liquid, it typically contains 10 to the power 22 to 10 to the power 23 particles. Similarly, if you take 1 mole of gas, you know that it contains Avogadro number of atoms or molecule. Avogadro number is a huge number, which is 6.023 into 10 to the power 23. So when you are talking about thermodynamic system, you are talking about system which contains large number of particles. Right? So in such cases, it's almost impossible to go to each individual atom or molecule and try to understand their microscopic properties. So in such cases, it makes more sense to understand the average property of the system, and that's where thermodynamics come into picture. Now, before going into the depth of thermodynamics, let's get first familiarized with a few fundamental concepts and terminologies. First one is thermodynamic system. It's a volume in space or well-defined set of matter under study around which one can draw a boundary. The boundary may be fixed, movable, or even imaginary. And everything outside the boundary is called surrounding. So here you have a system and there is a surrounding here, and these two are separated by the boundary. And the boundary plays an important role in thermodynamic interactions because energy and matter can be exchanged across the boundary. As I said earlier, thermodynamic systems are usually macroscopic systems which contain large number of particles. Next is thermodynamic variables and equation of state. How do you characterize a thermodynamic system, or how do you characterize the state of a system? Now, what is the state? Suppose you have a piece of ice. You are supplying heat energy to it. It gets melted, it becomes water. You supply heat energy further, it becomes vapor, right? So the state has changed from solid to liquid to vapor. So this is one way of looking at state. Similarly, you take a balloon which is not inflated, and when you pump air into it, it gets inflated. It becomes bigger. It's going to occupy a higher volume. Right? So initially you have almost nil volume. Now you are having something which is occupying a larger volume. So this is also another way of looking at a state. Okay. In terms of volume, you can look at the state. So basically you need certain parameters, certain experimentally measurable parameters, you call them as observables, to characterize any thermodynamic state. The typically used thermodynamic variables are composition, pressure, volume, and temperature. So using these 4 parameters, you can characterize a thermodynamic state. When I say state, I am exclusively meaning macroscopic state, because you can also have microscopic state, but that is the realm of statistical mechanics. In thermodynamics, usually we talk about homogeneous systems. For example, when I say I have 1 mole of oxygen molecules, each individual atom, oxygen atom or molecule are identical, right? So this is a homogeneous system where the composition is fixed. So I don't have to bother about composition. So when I say state variables, I mean pressure, volume, and temperature. So any thermodynamic system or any thermodynamic state can be completely described or characterized using these 3 variables. Now when you write a function of these three variables equated to 0, this is known as state function or equation of state. For example, in the case of ideal gas, I know PV equal to nRT, or I can write PV minus nRT equal to 0. This is the equation of state of an ideal gas. As you can notice from this equation, these three state variables are not completely independent. If you find out the values of any two of these, the third one you can calculate. So there is an inherent relation between these three state variables. There are also other thermodynamic variables like chemical potential, entropy, etc. But to define a state, these three variables are good enough. And usually you write the equation of state when your thermodynamic system is under thermal equilibrium. Now, what are the different types of systems? One type is open system, where the system exchanges matter and energy with the surrounding. For example, you can consider hot water taken in an open beaker. As you can notice, water vapor escapes through the opening, so matter is exchanged between the system, which is your hot water, and the surrounding, which is the air outside. Here, flask act as a boundary. Right. On the other hand, in addition to water vapor being exchanged, you also have heat exchange between the flask and the surrounding, right? That's why even though you have taken hot water inside, after some time you will notice that the water had come down to the room temperature, because heat is transferred from the water to the surroundings. So exchange of mass and heat both happen here, and this is the example of an open system. On the other hand, if you close this flask, what happens? Water vapor no more escape from the system, so exchange of mass is prohibited, but only heat is transferred between the system and surroundings. So this is a case of a closed system, which exchanges only energy and not matter. You also have isolated system, where the system neither exchanges matter nor exchanges energy with the surrounding. For example, you take a closed beaker and put it inside a thermal isolation, like a thermal flask. Since the opening is closed here, water vapor cannot escape from the beaker. Similarly, since there is a thermal isolation, heat is also not exchanged between the system and surroundings. So this is an isolated system. Thermodynamics in general is governed by three fundamental laws, which are the zeroth law, first law, and second law. This is very similar to the classical mechanics, which is governed by the three equations of motion given by Isaac Newton. Let's first talk about the zeroth law of thermodynamics, which primarily introduces the concept of heat and thermal equilibrium. Suppose you have two objects, one hot object and a cold object. If you put them in thermal contact, you will notice that the heat is transferred from the hot object to cold object till the temperature of these two objects become equal, where you can say that these two objects are in thermal equilibrium. So here energy is exchanged, or energy is transferred in the form of heat. So I can define heat as energy in transit. Okay. So the heat transfer will continue to happen till a thermal equilibrium is established. So zeroth law talks about the heat and thermal equilibrium. So it states that if two bodies A and B are each in equilibrium with a third body C, then A and B are also in thermal equilibrium with each other. So you have three objects A, B, C. A is in equilibrium with C, B is also in equilibrium with C, which means that all the three bodies are in thermal contact. So there is an inherent heat transfer between these three bodies, which makes sure that A and B are also in thermal equilibrium. Now, what is a thermodynamic equilibrium? So I can say that a thermodynamic system is in a state of equilibrium when two of the three thermodynamic variables, pressure, volume, and temperature, remain constant as long as the external conditions do not change. A system under thermodynamic equilibrium must satisfy three following equilibriums. First one, mechanical equilibrium, where there is no macroscopic movement of particles within the system or between the system and the surrounding. It should also satisfy thermal equilibrium, where there is no temperature difference between different parts of the system or between the system and the surrounding. Finally, it should also have chemical equilibrium, where there is no chemical reaction happening within the system, and also there is no macroscopic movement of chemical constituents within the system or between the system and surroundings. So once you have these three equilibrium, you can say that your thermodynamic state is in a condition of thermodynamic equilibrium. Another important terminology we need to familiarize is quasi-static process. Quasi means almost. So this is a process which is almost static. It appears that there is nothing is happening in the system, but in fact some very slow changes are taking place. Now, quasi-static processes are infinitely slow processes where the deviation from the thermodynamic equilibrium is infinitesimal. Infinitesimal means extremely small. Take for example water contained in a thermal flask. You know that this is an isolated system where there is no exchange of matter or energy. But in reality, you will notice that even though you have kept hot water in a flask, after a few hours the temperature of the water had decreased, right? Or if you keep it overnight or a couple of days, the water would come to the room temperature. But if you look at if you take hot water in a thermal flask, measure the temperature, after 1 minute, once again you make a measurement of the temperature, you don't notice much difference in temperature, right? Proceed 1 more minute, once again you measure the temperature, once again you don't notice an appreciable change in temperature. So it appears that these two measurements are almost in equilibrium, or if you are going to define it as a state, the state of the hot water after 1 minute or after 2 minutes is almost similar. So you can say that they are almost in thermal equilibrium. So this is what we mean by a quasi-static process. All the states through which the system passes through during a quasi-static process can be considered to be equilibrium states. You can consider another example here. Suppose you have a cylinder in which some gas is kept using a piston. Then you keep a weight on the piston. What happens? Piston comes down, the gas gets compressed. So you have a system which is occupying a smaller volume and having higher pressure. Okay, so you can call it as initial state of the gas system. You have high pressure but small volume. Now, if you remove this weight, suddenly what happens? Immediately the piston goes up, touches this point. So the volume of the gas is going to increase suddenly. Consequently, the pressure is going to decrease. Right? So you have the final state where the volume is larger but pressure is lower. So you have two states, and the change happens so suddenly that if you look at two consecutive states of the system, they are never in thermal equilibrium or thermodynamic equilibrium. Now imagine the scenario that you are removing the weight gradually. Suppose you have 1 kilogram weight here. You are going to remove 1 microgram at a time. Okay. So you remove the first 1 microgram and measure the pressure and volume. There is almost no change in pressure and volume, right? So you remove 1 more microgram monitor the pressure and volume, once again there is no change, right? So it appears as though these 2 points are almost in equilibrium condition, right? So you do this over a period of several days and finally you reach the final state. So even though there is a gradient here, look at the time domain. The time domain is infinitely long, right? So in such an infinitely long time domain, you can consider that each of these states are in thermal equilibrium. So such an infinitely slow process is known as quasi-static process. This is a hypothetical consideration. Usually none of the processes which we encounter in our day-to-day life is a quasi-static process. Finally, coming to internal energy, which is the total energy content of the system, it has three important components. One is kinetic energy, which arises due to rotation, vibration, and translation of molecules. Kinetic energy is temperature dependent. Usually, when you increase the temperature, the velocity of movement is going to increase, and consequently, the kinetic energy is also going to increase. Next component is the potential energy, which arises due to intermolecular forces that depends on the separation distance between the molecule. Probably you are familiar with the concept of electrostatic potential, right? Which is 1 by 4 pi epsilon naught Q by R. So potential energy has a 1 by R dependence, which means when R or the separation increases, the energy is going to decrease. The third component is the energy of electrons and nuclei. Now, one problem with internal energy is that I cannot measure the absolute magnitude of the internal energy. I can only measure the change in internal energy, delta U. So imagine that I have a system which is in state 1, the corresponding internal energy is U1. Now I am going to supply some heat energy Q to it, and also I am going to do some work on the system. So let W be the work done by the system. Sorry, there is a typo here. This is work done by the system. Okay. So Q is the energy supplied to the system, W is the work done by the system. And because of these two, system changes from state 1 to state 2. In state 2, the internal energy is U2. Now, what is the total change in internal energy during this process? So, total change in internal energy is final internal energy U2 minus initial internal energy U1, which is Q minus W. Don't bother about how this equation is derived. You are going to deal with it in detail when we discuss about the first law of thermodynamics. For now, just know that the internal energy is inherently related to heat and work done, and it has a contribution from kinetic energy, potential energy, and the nuclear energy. That's for today. In the next class, we will discuss about various thermodynamic processes. Thank you.